computational epidemiology at Virginia Tech. And this talk is going to be a little bit of a hodgepodge of why you should be interested in epidemiology, why you should be interested in the package I wrote for epidemiology called Epipy, and also a little bit about a visualization I developed to look at outbreak data. Thank you. Okay, so first of all, epidemiology is concerned with the 5 W's, who, what, when, where, and why of disease. It's a mix of biostatistics, medicine, and some good old-fashioned detective work. And like I said, I'm an epidemiologist, and so I wrote a package called Epipy that include Python tools for epidemiology. There's a fairly robust epidemiology community within R, but there's almost nothing in Python. So just a little bit more about why you should be interested in epidemiology. Public health has done great things for the whole world. This is a plot of the incidence of, the crude death rate of infectious diseases over time. And you can see not only a clear trend, but you can see where different public health interventions really made a huge impact on the health of the public. Things like smallpox eradication, our near eradication of polio, these are huge, huge accomplishments. And why I got interested in embarking on this project came from a modeling project I was doing of Middle East respiratory syndrome coronavirus, which is a new SARS-like coronavirus that's emerging in the Middle East. And it's kind of a weird disease. It affects more men than women, especially older men, especially people with comorbidities. And one of the reasons we're interested in it is it has a very high case fatality risk. So right now, somewhere between 30 and 40% of the cases that we identify die, which is huge. We think it comes from camels. You don't actually have to kiss the camels, but I thought it was striking that there were so many opportunities to include these pictures. The disease right now is primarily in Saudi Arabia, and their camels are sort of pets, so this is apparently something people do quite often. So one of the features about MERS is it's an emerging zoonosis, which is the sort of disease class that I study in particular. There are 4 different stages of emerging zoonoses. The first just affects animals. The second can infect a human, but then the human cannot go on to spread it. MERS is a stage 3 pathogen, which means it can create stuttering chains. So an animal can infect a human, that human can infect 1 or 2 other people, but eventually it's going to die out and it's not going to become sustained. Whereas stage 4 pathogens can cause pandemic illness. An example of that would be influenza. So MERS is a stage 3 pathogen. It causes stuttering chains. Now, the reason we're interested in diseases that just can infect a couple people in the beginning is that they can mutate to become a much bigger problem. So this is an epicurve of SARS. An epicurve is just a histogram of new cases over time. And you can see in the beginning it wasn't that big of a deal. There were certainly cases, but it wasn't the widespread thing that it came to be. So one of my goals is to identify which diseases are going to go on to become the next SARS, for example. So the way epidemiologists usually handle data is with a line listing, and that's just simply a spreadsheet of all of the cases that you've identified and relevant information about those cases. So their age, their sex, maybe possible exposures, like did they eat the potato salad, for example. And the line listing is useful for a bunch of different things, but it's not so useful for identifying networks. So you might have a column that says case contact number, and it might say what contact person 1 met with person 3, and person 3 met with 4. And when you have 100 of those, it becomes really confusing. And this was the situation with MERS, as I had a line listing of all of the cases, but it was getting up into the hundreds, and I no longer had any clue how big the stuttering chains were, how many cases were in each cluster, and so on. So I developed a case tree plot, which is, I guess, the point of this talk. On the x-axis is time, and the y-axis is generation, where a generation is sort of the next person in the chain who got it. And these are just networks along time. Nodes along the x-axis are index nodes, is what I call them, and there are cases that are suspected of having been acquired from animals. Cases along subsequent generations were acquired from humans. And in this case, in MERS, I see generations up to about 5, but it kind of depends on how you tweak the parameters. And so just to talk a little bit more about case tree uses, what they are, why you might find them useful. First of all, you can get a good sense of the basic reproduction number from case tree plots, and this is probably the most central value in epidemiology. You might also hear it referred to as R0, and it's simply the average number of secondary cases from each case. So if I'm sick and I give the disease to 2 other people, that would be an R0 of 2, but of course we're talking on populations, so it's more of an average. Just by looking at the case tree plots, you can get an idea of if you're looking at an R0 of 0.5, which is no big deal, or 2, which is a really big deal because that's something that could continue to pass and pass and pass and pass. There are also some built-in functions with the case tree plot where you can examine the reproduction number a little bit more. So you can look at a histogram of the distribution, and then you can look at summary statistics of the size of the trees. You can also look at the changes in epidemiology over time, and if you recall what I said about SARS, we're really interested in learning how diseases change over time, because if something is going to become more human-to-human transmissible, we want to know that early. So you can see on the left here, there's some indication, this is just simulated data, that this disease is becoming more human-to-human transmissible, whereas the other plot, not so much. There's not such of a pattern there. You might also be interested in the frequency of zoonotic spillover. Once again, zoonoses is just a disease acquired from an animal, so it's animal contact. Both of these plots have about the same number of nodes, but they're structured very differently. So if you see a plot that has, for the same time frame, 100 different spillovers, you might be looking at something that's a domestic animal, for example, something people come in contact with a lot. If you look at a plot with just a couple spillovers, it might be more of a rare animal, like a bat, for example. You can also look at case attributes by generation. So normally I color the trees just by what cluster they belong to. But you can choose to color them by case attributes. For example, if they're male or female, you might be interested in the status of the case, so whether they're alive or dead. So in this case, which is once again just simulated data, all of the index nodes are male. So that might suggest that the disease comes from something that men are in contact with more than females. So hunting, for example, maybe it's a deer-borne disease. And once again, you can look at the distribution of the case attribute over the generations. So several inferences that I learned from developing a case tree plot about MERS. One is that the basic reproduction number of diagnosed cases is relatively low. It's most likely below 1, which is borne out with modeling studies and different inquiries. And that's really important because for reproduction numbers above 1, it has significant pandemic potential. I also have seen that the frequency of spillover has some seasonal component. So we've gone through 2 years of the disease, and each time April has been a really huge spike in cases. And we think that that might be because of the camel breeding season, but looking at the case tree plot, if you hadn't already spotted that trend, you might be able to get some insight. And finally, there have been a couple super spreading events, and by that I just mean a more than expected number of transmissions. So you can see there are a couple trees there with way more nodes than the other ones. That would be something we would want to look at. Other uses for Epipy apart from case trees. There are several that are common to epidemiology, things like odd ratios, relative risk, diagnostic summary. I also have stratified summary statistics, so you can look at, for example, the age of cases by whether they're male or female, just for simple comparison. You can look at case attributes by generation and so on, and you can also simulate your own data, so you can simulate line listings, and you can say how many generations you want the clusters to be, you can input your time frame and so on. So you can play with these values yourself and see how the outbreak changes. You can also make your own epicurves, which is not a huge deal. It's just a histogram of cases over time. But epicurves are traditionally bar plots and not line plots, so it becomes kind of tricky to work with the matplotlib time series. You can do it by day, month, or year. There's also a plot that complements the case tree plot. I'm calling it a checkerboard plot, and it's once again just the cases in a cluster over time, but instead of trying to determine the configuration, which case tree does automatically, it simply puts them on a time series. So if you're not comfortable trying to configure a tree, then this might be a good alternative. You can also, the plot on the right there, I'm sorry, didn't render very well, but it's odds ratios with 95% confidence intervals. So if you want to know, for example, risk factors for getting sick, then you might want to know the odds ratio, and that's something that you can plot. Finally, this is just in the GitHub version. It hasn't been pushed out yet, but you can look at the rolling proportion. So these are 30-day rolling proportions of various categorical risk factors, for example, male or female, whether you're a healthcare worker or not. And these are 30-day rolling proportions, but you can configure what time window you want. And it's interesting for looking at changes in the disease over time. There are a couple other Python tools for epidemiology, and the good news is we're pretty much all here. There's Epipy, there's Pico, which is also a package I wrote, and it's simply a wrapper to access nationally notifiable disease data. There's Epigraphs, which simulates contagions over networks. There's Zeek, which some of you may have seen earlier in the year by Eric Lofgren. It's used to model zombie epidemics as a teaching tool. And there's also pump handle, which is pre-development, but it has a README, so someday. And that concludes my talk. Thank you.
Thank you, Caitlin. Other questions?